Hello everyone, my name is Yichen Lin. I'm the co-author of this work with Bingyi Zhang. Our advisor is Viktor Prasanna. Today, I'm going to present our work, HP-GNN, generating high-throughput GNN training implementation on CPU-FPGA heterogeneous platform. I would like to start with some backgrounds in graph neural networks and the acceleration challenges. And then we will move on to how do we address these challenges and the experimental results. So first, what does a graph neural network do? A graph neural network can embed node features and graph structures into a low-dimensional vector, or what we call node embeddings. And the reason why this is important or why this is useful is because with these node embeddings, we can facilitate many downstream applications to do node classifications, link prediction, and clustering. These tasks are usually used in social recommendation systems, traffic forecasting, and protein analysis. There are two major approaches to construct a graph neural network. The first one is very intuitive. With given an input graph, we can take all the vertices and edges to construct a full batch graph neural network. But this approach is inefficient as graph grows larger, because as graph grows larger, it is very hard for a full batch GNN to fit into a GPU memory, and this slows down the training. In recent works, many sampling-based graph neural networks algorithms has been proposed. So the idea is, instead of taking the entire graph, we will only sample several vertices and several edges to construct our neural network. This is called the sampling-based GNN, which is also the focus of our work. Next, why do we need to do acceleration? Well, as I mentioned before, graphs are becoming larger. So to deal with these very large graphs, it usually took a long time to do training, maybe hours to even days. And in terms of inferencing, some of the applications like traffic prediction will require real-time inferencing. So we will also need to do accelerations. There are many challenges when it comes to accelerating graph neural networks. First, graphs are very sparse data. And so when we're doing GNN computation, it usually suffers from poor data reuse and random memory access. Also, GNN computation consists of very different characteristics. There are two major steps. The first is feature aggregation, which usually is very communication intensive. On the other hand, feature update is usually computation intensive. So in order to achieve good performance, we need to deal with these two very different characteristics of GNN computation. Luckily, the first two challenges has been widely studied in recent years. Many of these previous work have accelerated GNN on CPU-FPGA platform. There are several reasons. For example, FPGAs are very ideal for computation-intensive works like matrix multiplication. We can implement systolic array-based designs to do very fast matrix multiplication. Also, FPGA supports customizable data path and has large on-chip memory. This feature can be utilized to deal with the poor data reuse and random memory access problem. So works like GraphAct, BoostGCN, Deep Learning GL has been proposed to accelerate maybe training or GNN inferencing. Although there are many works that has been done, some challenges remains. In this work, we can see that there's no one-size-fits-all GNN model. In other words, different GNN models outperform each other in different applications. So for some applications, Model A performs better, and for other applications, Model B might perform better. And this becomes a limitation of previous works because these previous works, they either focus on a specific model or maybe a specific sampling algorithm. Also, their optimizations are not applicable to other models. So the problem is, if I want to utilize a model, but that model was not being accelerated before, I could not directly utilize these previous works. And this becomes a limitation. Also, if I want to develop my own accelerator, it will require hardware expertise. I will have to know maybe Verilog or HLS programming. I need to know how to do design space exploration to fully utilize our resources. And last but not least, it will take maybe weeks of development efforts to do coding and optimizations. So we found that there's no generic framework that can accelerate various sampling-based GNN training, which motivates us to conduct this work. We want to propose a general framework that can support different GNN models, not just a specific model or a specific kind of sampling algorithm. We want to abstract away the hardware implementation detail and make it accessible to users who might not have backgrounds in hardware development. So the first problem is, how do we support various GNN models? We start by first trying to capture the computation abstraction of GNN layer. So even though there are a lot of different models, but all these GNN models, they follow very similar computation abstraction. For each layer, it follows the architecture, which first does a feature aggregate, followed by feature update, and then followed by element-wise activation function. And these different models, they can be specified using some of the key parameters. So by capturing different models using the same computation abstraction, we can develop hardware template. This hardware template is based on a GNN computation abstraction instead of a specific model. So for example, what we're looking at here is the aggregate kernel template. Our template is a general architecture that describes how different hardware components are connected, how the data flows, and instead of a specific model. So the processing element, for example, the scatter PE and gather PE, are left for users to define their own scatter-gather functions. So by doing so, user can define their own GNN model. We also apply several optimization for the aggregate kernel. As I mentioned before, feature aggregate is usually very communication intensive. In fact, aggregate is one of the most time-consuming steps in GNN computations. Our first optimization is reducing memory traffic in the first GNN layer, which it needs to fetch features from the memory. So we can observe that for different ages, they might have the same source vertices. So for example, if we look at these two edges over here, they both fetch the feature from vertices V1. So what we can do is, for these kind of edges, we will present data reuse to reduce the memory traffic. So for this case, we do not need to fetch the same feature vector twice. Instead, we only need to fetch it once. We will also present renaming and sorting. So for layer 2 and above, we can avoid random access because after renaming and sorting, the vertices number will match the order of how it is stored in the memory. These optimizations needs to stay general so they can be applied to different GNN models. We also designed the update kernel template, which is a state-solid array-based design, and user can customize the activation function. At last, we will have several kernels, and they will be distributed to the multiple dies on FPGA and connected to all the DDR banks. So now we have our hardware template or HLS template designed based on the GNN computation abstractions. Users will specify the key parameters using our APIs, and these information will be merged to the HLS template. So information such as scatter function, gather function, and so on and so forth, and to produce a kernel. The next step is now we have a single kernel design. We want to fully utilize the FPGA resources. So what we will do is we want to do design space exploration to see like how much kernels can we implement. As mentioned before, we want to make this work accessible to users who might not have hardware backgrounds. So we want to automate the design space exploration step as well. We do so by building a DSE engine. The DSE engine, well, what it do is that given some GNN parameters specified by the APIs and the platform metadata, it will perform DSE automatically and produces hardware configurations that can optimize the throughput. For our example over here, it will produce two parameters, N and M, which stands for the parallelism of the aggregate kernel and the update kernel. The DSE engine consists of two major components. The first is resource utilization model. So for deciding the parallelism, with more parallelism, we of course will use more resources. We identified that the two mostly used resources in our design is DSP and lookup tables. So we formulate the resource utilization. So doing the DSE, the number N and M, it will decide how much, we will estimate how much resource we need. And of course, this number cannot exceed the available DSP and lookup table we have on the FPGA. The second component is the performance model. So we evaluate our performance using throughput, and we define the throughput as number of vertices traversed per second. And the denominator, time of execution, is the average execution time of a mini bash. And you can imagine is a function of N and M because when more parallelism are implemented, you can expect the throughput to become higher. So with these two components, what the DSE engine do is that it will perform a parameter sweep by trying different combinations of N and M and see which configurations might be able to provide us the best throughput. So now we have the single kernel design, and we can decide the acceleration configuration. We are able to produce the accelerator design. And of course, we also have the software generator, which consists of the sampler and host program template to produce a host program that runs on a CPU. Here we're showing some example input-output of our framework. So on the left side is the user input, specifying some GNN parameters using the APIs, and the right side are the produced codes. For example, over here, we can see that the user specified a two-layer model, and this parameter will reflect on the right side So looking over here, which is the generated host program, we can see that, for example, for a 2-layer model, we need to run 2 iterations and for the code. So over here, the variable layer will be 2. We can look over here where we're trying to decide the custom layer operator. The user specify using an add for the gather function. And so for the produce accelerated code, we will see the add over here. And we also perform DSE to decide the hardware configurations, and that will affect the accelerated code. So for example, the unroll factor over here is decided by the DSE engine. This is our experimental setup. We evaluate our framework using Xilinx Avio U250, which has 77 gigabytes per second of bandwidth. We implemented our codes using high-level synthesis and place and route using bias. We tested 4 application settings using neighbor sampling-based algorithm and subgraph sampling-based algorithm, combined with 2 models, GCN and GraphSage. Here we show the resource utilizations for these 4 different application settings. And as we can see, the lookup tables and DSP are mostly used. We implemented our baseline using PyTorch geometric and run it on CPU-only platform and CPU-GPU platform. We chose 4 data sets from social networks and e-commerce. And we can look at the experimental results. We compare the throughput to our baselines and using 4 application settings. And we can see that the accelerator generated by our framework achieved around 55 times speedup over a CPU-only platform and around 2 times speedup over a CPU-GPU platform. We also compare our work with some state-of-the-art accelerators like GraphAct and Rubik, and our accelerator can achieve around 3 to 4 times speedup. So in conclusion, we designed a general framework. Given GNN parameters and platform data, we can generate high throughput GNN training accelerators on CPU-FPGA platform. So thanks for your listening. If you have further questions, you can contact me via this email or visit our websites. Thank you.